Okay. Well, it is 9 a.m. So good morning, and I'm gonna send an email if I don't forget. So you should check your grades. By now you should have all 6 grades, and if any grade is missing, just send me an email. And we are continuing our discussion of the Doppler effect. So please, what do you think? Sound wave travels away from a source in the same direction the source moves. Doesn't always have to be that way, because sound waves travel away from a source in all directions, and when the source is traveling, that may affect the wavelength of the sound wave it generates. Relative to whom? Well, relative to somebody who is listening to that sound, who is registering that wave. And what is happening when a wave is traveling through a location of an observer? Would have been just a microphone. So as we know, a wave is a combination of wave fronts. So if we have a, how to draw it, an ear, well, the ear usually belongs to a head. That's all we need, an ear and a head with a brain connected. So the pressure at the location of the membrane changes, and every pulse, we can describe as just a push. And what is a frequency? The frequency is the number of those pushes per second, basically. Well, and the wavelength is a distance. So the frequency, the number of pushes per second. And these variables are also related to how fast the wave is traveling relative to that person. So these 3 variables are related. Frequency, wavelength, speed of the sound. They all have to be measured by the same person, an observer. That's very important. This observer might be at rest relative to the ground. This observer might be moving. It doesn't matter for this situation. And all we need to remember that when source is moving, it generates the next front at a next location, at a different location. So this is the first time when a certain front is generated. It takes a certain time to move away from this location. So if we wait long enough, that's the same front, but at different time. So we have 2 pictures put together. Picture number 1 relates to one time, picture number 2 relates to a different time, but the second picture also should show the new location of the source, because the source was also moving during the same time. And the easiest way is to think that we waited exactly one period, which means now a new front starts traveling away, and the distance between two adjacent fronts, that's what the wavelength is. So the answer to this question is in front of the moving source, wavelength shrinks, but behind the moving source, wavelength expands. And where should the observer be located in order to experience the drop in the frequency? Behind. The drop in the frequency is related to expansion of the wavelength. So an observer here should experience the sound with a lower frequency. Lower than what? When we say lower, higher, we always make an assumption relative to something. There's always an assumption, like if we say the car drives at 35 miles per hour, there's an assumption that it's relative to the ground, this ground, the earth. So when we say frequency changes, we mean relative to a situation when nothing and no one would have been moving at all. Not the source, not the observer. In that case, of course, the observer registers specific frequency, but when the source begins moving or observer begins moving or both, that frequency might go up or down as measured by an observer. Well, this is the second question. It's related to an observer. And in this situation, actually two observers. One is at rest relative to the car. The car and the first observer are on the ground, resting. That's what we call a stationary situation. However, there is a second observer, someone else, and that person runs. How can it run? Well, we only consider one-dimensional situation. So a moving observer can travel toward a source or away. Does it matter? Yes, it matters. In this situation, an observer travels toward the source. But we don't care about the source. Again, all we care about the wave it generates. So we have to see those waves. That's how they travel. Front number one, front number two. They travel all together with the same speed, which is the speed of the sound relative to the ground, about 320. However, so this is the speed of the sound relative to the ground. But we would never, ever use this whole subscript speed of the sound relative to the ground. Too much work. That's why we just use this letter. But we mean speed of the sound relative to the ground. However, when the observer runs, that doesn't look like running, runs, and this variable represents the speed of the observer relative to the ground. But again, we would never write all the speed of the observer relative to the ground. We have to remember that. That changes the speed of the sound relative to the observer, according to our PY105 consideration. Again, if we use the law of relative velocities, which we used yesterday, it says the speed of the third object relative to the first is equal to the vectorial sum of the speed of the third object relative to the second plus the speed of the second object relative to the first. In this expression, all variables are arrows, vectors, and the numbers represent any three objects in the universe. Any. 1, 2, 3. Column, grass, tree, plane, airplane, observer, water, shore, any three objects. But those vectors have magnitudes, and if we switch from vectors to magnitudes, equations depend on the mutual orientation, mutual motion of mutual orientation of velocities. So in this situation, the speed of this, well, speed, now I gotta use some extra letters. Speed of the sound relative to the observer, it should be equal to the speed of the sound relative to the ground plus the speed of the observer relative to the ground, because they close to each other faster than it would have been if the observer would have been at rest. But the question is not about this. The question is about measuring distance between two objects. Well, in this situation, the object number one is one front, the object number two, the second front. And what do we use to measure distances? Rulers, meter sticks. So we place it and read the number. And it doesn't matter if we are moving or not, unless we're moving very, very fast, which is never is the topic of this course. Special relativity theory would affect the measurement. But in real life for us, when we measure this distance using a meter stick, we just have to read two numbers. And it doesn't matter if we move or at rest, we read the same numbers. So the answer is, I had a slide. Oh, same. Same means 1 meter. These are things we have to remember. So, yes, 1 meter. And again, just for curious people, there is a algebraical derivation of everything we've said before to get to the Doppler effect equation. We did this part when the source was not moving. We did that part when the observer was not moving. And we know that when they move together, the frequency has to be affected by both reasons. So again, all we need to know is this equation, Doppler effect equation, and all we need to know what to do about it is when to choose a plus, when to choose a minus. And for the source part, for the denominator of this fraction, first we have to remember in mathematics fraction changes when we change the numerator or denominator. How does the fraction change? If we increase the denominator, the fraction decreases. If we decrease the denominator, the whole fraction increases. With the numerator, it's much easier, right? So, source. If the source is not moving, this variable, the speed of the source relative to the ground, Vs, is just 0. When the source is moving, well, that was the question number 2 today. When wave fronts are in front of the moving source, wave length shrinks. That makes frequency higher. To achieve that, we have to decrease the denominator. To achieve that, we have to choose a minus. Otherwise, what does it mean otherwise? It means that we're looking at the wave traveling behind the moving source. Wavelength expands, frequency goes down. So the frequency experienced by the observer should be lower than the frequency for the stationary situation. To achieve that, we have to increase the denominator. To achieve that, we have to choose a plus. For the observer, what do we do? Well, for the observer, we know that when observer and waves travel toward each other, the frequency goes up. Why? Well, basically, again, what is the frequency? It's the number of pushes on the ear membrane per second. So if you have a resting observer lying down on the ground, so one wave travels through, second, third, we can count how many waves travel through the location, this location, that's the ear, per second. But if an observer travels, runs, this guy will hit more wavefronts per second. That's it. And that's what frequency is. Frequency should go up for this situation. So the velocity, frequency goes up. To achieve that, we have to increase the fraction. To achieve that, we have to choose a plus in the numerator. Otherwise, what does it mean, otherwise? Where should the observer be? Not here, because this sound wave wouldn't reach that guy. That should be the same observer, but now it should travel in the same direction with the waves. And in that case, we should choose a minus. And now we know everything. Well, technically, we knew everything from yesterday. Now we know everything one more time. And this is the standard strategy for any problem related to Doppler effect. And of course, it starts from a picture because we should see how the source travels, how waves travel, how an observer travels. And then we should, based on the picture, choose plus or minus for numerator, for denominator, and solve it. What does it mean, some extras? Well, for example, we know that the wavelength of the wave depends on the motion of the source. So we can relate the wavelength in one situation, when the source is at rest, with the wavelength when the source is traveling. That's an additional equation. And the equation, well, again, just to remind, the new wavelength is equal to old plus or minus distance traveled by the source during one period. When do we choose a minus? When the wavelength shrinks. When we do so for waves in front of the source. When do we choose a plus? When the wavelength expands, which means for the waves behind the source again. Well, this is just one of the examples. Now, practicing. I'm going to give you some time to finish just the first one. What does it mean? Well, so in all these four situations, and physically there might be more, the source, well, wherever you read in the left column is physically located to the left to wherever you read in the right column. And those arrows represent how they move. So for example, let's call them case number 1, case number 2, case number 3, case number 4. What else could happen? Well, directions might differ. So for the case number 1, the source is to the left to the observer, and they both move relative to the ground to the right. That's what it means. And now you have to choose. The top means in the numerator of this fraction, and the bottom means in the denominator of this fraction. You have to choose a plus or a minus for each of these cells. I'll be back. I'll give you your privacy. Bless you. I'm back. Let's vote. So, a plus or a minus? A plus or a minus? All right, come back. So if you think the top sign is a plus, please raise your hand. So everybody thinks it's a minus. Still, if you think it's a minus, please raise your hand. You're like, oh, whatever. An observer. So when we talk about an observer, we have to look not on the source, we have to look how the waves move. So we have to add one more element, and you should have done it. Waves, wavefronts. Wavefronts travel in all directions away from the source, but we don't care about those. They do not reach the observer. We only care about those which reach the observer, these ones. Why? Why do they reach the observer? Because they travel faster. 330 meters per second. No person can run that fast. If the person would have been running faster, that would be supersonic. So eventually it happens, and in this situation the frequency from the observer's point of view should go down, and when we say down we mean relative to the situation when nothing is moving at all. And to do that we have to decrease the denominator, and to do that we have to use a minus. Yeah. So now we can move on to this part, this part. So in front of the source, the wavelength shrinks, the frequency I don't know, SO, because standard symbol like this one, Fs, represents stationary frequency when nothing is moving at all. So the frequency due to the source should go up, and to do that we should choose a minus again, because this is how we increase the fraction. All right. Okay, so you do your part, I'm going to do my part. Second case, now we have an observer here, and the observer travels to the right again, but source is here. So we switched the locations. What does it mean in terms of frequencies and wavelength? Well, again, we need to look at the wavefronts which reach the observer. These wavefronts reach the observer. And so that's the VO, VS, V. Now what do we see? Now an observer and the wavefronts travel toward each other. So a plus. However, behind the moving source, wavelength increases, so a plus. Wavelength increases, frequency decreases. So case number three. We have a source, we have an observer, and they travel away from each other, source and observer. What fronts do we have to see? Those which reach the observer. So this is what we call behind the source. The wavelength expands. So for the source, we should choose a plus. And these travel in the same direction. So frequency should go down, a minus. Case number 4. And I hope I haven't made any mistakes. But if I made a mistake, you should tell me now or never. And now we have an observer here and a source here. And they travel toward each other. So wavefronts which travel toward the observer and reach the guy travel, how do we call this direction? To the left relative to us. Yeah? So that's VO, that's VS, that's just V. Those variables represent speeds in equations. And if we look at this situation, source and wave fronts, they travel in the same direction, which means in front of the source. And to do that, we have to account for that. So wavelength shrinks, frequency increases. We should choose a minus here. And a plus here. An observer and wavefronts closing. Frequency goes up. After this, all we have to do, if we have to solve a specific problem, just plug the numbers in and use those numbers. Question. So, a child, probably a son or a daughter of a physicist, studies the Doppler effect, have stolen a speaker from a physicist, a father or a mother. It's gender neutral, it could be either, maybe both. So, when the child is moving, that's an observer moving relative to a stationary source. So, of course, he or she will be experiencing the change in the pitch, the change in the frequency. And the question is, at which location of these 5 locations the frequency experienced by this guy will be the highest possible and the lowest possible? First of all, there are locations which we can immediately exclude. Those are locations where it stops momentarily. That's a simple harmonic motion, a pendulum. Where does the pendulum stop? At which point? for example, at the point number 1 or at the point number 2. So because the speaker is not moving, here and here the speed of the observer equals 0 and the speed of the source equals 0. So because the speaker is not moving, this is 0. So that's why we need to look at the observer only. And to achieve the largest change, this guy should travel as fast as possible, at which location the maximum speed is achieved. That's a pendulum. So at the location number 3. Either way, yeah, when this guy travels toward the speaker, he experiences the sound with the highest possible pitch and away with the lowest. So for this direction we should choose a plus, for this direction we should choose a minus in that equation. All right, and now let's just solve several problems. So you have to read the problem and draw a picture. And for the picture A, so this situation, this text describes two situations, two problems in one. Problem number 1, when the train is approaching, what do we have to show in your picture? You have to show the source, how it moves, an observer, how it moves if it's moving, and wavefronts or waves traveling in a specific direction, those waves which reach the observer. So you have to draw that picture. Then you have to take a picture of that picture. And then you have to email the picture of your picture. Where? To whom? Not to a friend. Well, you can email it to your friend. Say, see what I'm doing right now. But you also have to email it to me. Just for the case now, case A. High-speed train. High-speed trains travel in Japan, China, Europe, but not in the US, by the way. There is a sentence, the speed of the sound is 343. This number represents a speed of the sound relative to something very specific. Relative to what? It's not there, but we have to know that. It's a standard assumption. 343 relative to what? Ground, yes. And 415 hertz, this frequency, again, assumed for what situation? For a stationary situation, when this train would be at rest and an observer measuring frequency of the sound would be at rest, that would be the number 415. That's what we call FS, frequency for the stationary case. And why do we need a picture? To choose a plus or a minus in the numerator and to choose a plus or a minus in a denominator. And well, ground 3. The 3 represents a stationary location because trees don't walk. And there's a train. which travels in which direction. You choose. There is no specification about the velocity. So, I don't know, for me, naturally, I choose to the right. What does approaching mean? For the case A, where should I place the observer? In front of the train, because that's what this word approaching means. Now, is the observer running? No, standing. See how words matter. So VO equals 0. VS, 44.7. Now, waves travel from the source in all directions, but we need to see only those which eventually would reach the observer. So this is that wave. These are the fronts of that wave. And, well, that's a picture. This is a stationary observer. No one can move when lying down. So now what do we do? Well, we just start plugging numbers. This is what we are looking for. This is a known frequency for the stationary case. So this is 1 plus or minus 0 divided by 343. And this is 1. 44.7 divided by 343. And now we have to choose a plus or a minus. And the denominator is not related to an observer. This is what we should look at. So the wavelength in front of the moving source shrinks. Hence, the frequency should go up. To make it going up, the denominator should go down. To make it less, we have to use a minus. That's it. Now, there is a different, on the equation sheet, actually, and in slides, there is a different equation for the same effect. Mathematically, those equations are identical, because what I can do, for example, I can just, here in this equation, multiply the numerator and the denominator by the speed of the sound. Or I could have done it algebraically by multiplying by V. So this equation might be just more convenient technically, easier calculations. So this is going to be 343 minus 44.7. This is going to be 343. And that's what we need to calculate. The result, of course, will be exactly the same. So 415 times 343 divided by, open parentheses, 343 minus 44.7, close parentheses, 477.2. What do we do to answer question B? We have to change a minus to a plus. That's it. So that's A, B, 415, 343, 343 plus 44.7. Whatever it is, that's the answer. So, solutions, and it was not, was it? What is the frequency and the wavelength? Okay. So, to calculate the wavelength, we've used an equation which relates speed, frequency, and wavelength. This equation can be written relative to the ground, 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 but the same equation can be written relative to the observer, observer, observer. So the wavelength will be equal to the speed of the sound relative to the observer, divided by the frequency of the sound measured by the observer. I don't want to use this versus this. Yeah. This symbol represents speed of the observer relative to the ground, and this symbol represents speed of the sound relative to the observer. Okay, sound relative to the observer, sound relative to the observer. But when the observer is at rest, those are different. When the observer is at rest, when this is 0, the speed of the sound relative to the ground and the speed of the sound relative to the observer, same number. So this is how we get the wavelength. The frequency has been calculated. The speed of the sound is 343. Done. Next problem. Stationary observer. Okay, so I'm going to read and draw the picture simultaneously. A stationary observer, an observer, stationary, finds, well, he's not sleeping, just laying down, that the fire truck makes a sound of a given wavelength in the air when approaching. Okay, so the fire truck is approaching. This word says travels toward the observer, and it makes a sound, and the wavelength, it's a mystery how the guy would measure it, but he did. The wavelength turns out to be 1/2 of a meter. The question is this a wavelength which we normally would use as a lambda or as a lambda prime? The answer is who cares? When we measure wavelength, moving observer or resting observer would measure the same result, but the source changes the wavelength. So this variable represents a situation when the source is not moving. This variable represents a situation when the source is moving. And, well, we know that the relationship between these should be equal to plus or minus distance traveled by the source in one period. Now, plus or a minus for this specific situation? What do you think? A plus or a minus? What should we choose? A minus, because in front of the source, the wavelength shrinks. So I have no idea if I want to use this relationship or not. I'm just writing down to make sure I understand what is happening. Now, distance traveled by the source in one period is equal to the speed of the source, time, which is one period. One period of what frequency? This or that? That's an important question. Stationary, So in order to make it sure we got it right, this is how we can write it down. Well, anyway, because the observer is at rest, our equation again is very simple. This one. And we have to choose a minus. Wavelength shrinks, frequency for the observer goes up. And what do we know? What do we know? The speed of the train relative to the ground. The speed of the sound relative to the ground. Okay, so if we use these numbers, we get this. Well, this equation has two unknowns, but what can we do to find something? Well, we know that there is another equation which we always can write down and then use it. This equation can be written again relative to different origins. For example, it can be written relative to the observer laying down on the ground. And because the observer is not moving, the speed of the sound relative to not moving observer is 340. The wavelength he measures is 0.5 because we can read. And now we have to write the frequency, but we have to choose the correct subscript. We have to choose between S or O. We choose it right, the problem is solved. We choose it wrong, we make a mistake. So, what should I write here? If you think I should write a letter S, please raise your hand. Don't do that. That's wrong. If you think O, write it down, because in this equation, everything including this number, measured, see, observer finds. So that's for observer, which means everything else should be for the observer. And this equation now tells us one missing variable. So 340 over 0.5, that 340 over times 2, 680 should be equal to frequency. And now I want to switch to an easier situation. So I multiply by 340 here, and here 340 minus 10. And that gives me a simpler equation, 340 over 330. And now I can solve it. The stationary frequency should be, I had to do it in my head, 680 over 340 is 2 times 330, 660. Which is lower than 680 as it's supposed to. If the track would not be moving, the frequency for the observer would be 660. And when the truck starts moving, the frequency goes up to 680. And well, when the truck is not moving, what is the wavelength of that sound? Well, we could have used this equation, but why? It's too complicated. We can write an equation again, which relates speed, wavelength, and frequency. But now we can add those variables, stationary, and now we can write numbers 340. That will be the wavelength we are looking for. This will be the frequency of the sound for the stationary case. Any questions? A new problem. So now the truck is not moving and observer is moving, so let's do it quickly. It actually should be easier than the previous one. So the source is at rest, but the observer is moving toward, could have been away, that matters, but in this situation toward the stationary truck. And the wavelength equals 0.5. Which one? Same. When the truck is not moving, it doesn't affect the wavelength, and when observer is running, it measures the same wavelength as it would have been measured by the resting observer. We should remember that. Waves travel like this. They have to reach the observer. So the speed of the sound is a given number, 340. So our equation, which relates frequencies, now we just have to do, well, actually, I want to write a fraction over 1, and that should be equal to 1 plus this ratio. Why is it plus? Because they travel toward each other. But of course, I want to rewrite it in the easier form. And now I can start plugging numbers in. 340, 340 plus 10. Again, that's it. But we always can add an additional equation when we need. We just have to write it specifically for, well, given the reference frame. And the wavelength is measured by the observer. So we have to write O. If we write this subscript for one variable, we have to write automatically the same to others. This is the frequency of the sound measured by the observer, and that's supposed to be the speed of the sound relative to the observer. Everything has to be relative to this observer. Well, this number is a half because we know it. This is an unknown. So if we want to solve this problem, we must say something about this number. What should I write? Well, what choices do I have? The natural choice is 340. What other possible choices do I have? Anyone? 10. What other possible choices do I have? 350 or 330. We make a right choice, we have it solved. We make a wrong choice, we make a mistake. So, well, in the order of appearance, if you think it's 340, please raise your hand. 10. 350. 330. Why would it be 330? Please tell me. Just your reasoning. Yeah. That's kinematics, has nothing to do to sound. You have one object number one, which travels to the left at 340 meters per second. You have an object number two, which travels to the right at 10 meters per second. So the speed of this object relative to this observer is equal to distance traveled over time. That's one situation. That's another situation. That's another situation. That's another situation. This is our situation. So please, out of all these situations, why is it 330? Why did you subtract? That doesn't answer my question. Why did you subtract? That's the equation. But it is a wrong equation. This is the equation from a perspective of you. You calculating speed from a perspective of a moving person. From that perspective, you are not moving because you're looking at yourself and you're not moving. The world is moving. So the earth is moving toward you, trees, bushes, and the sound is moving toward you. So if you want to use vector addition, you could use, but it also depends on how you look at it. Relative to the ground, they travel like this, but relative to the moving person is at rest, and everything travels toward that. So the right answer is 350, because if you look at two pictures, picture number one and the picture number two, when they're getting closer, and this is a perspective from the ground, from the person on the ground, but if you want to calculate the speed, what would we have to do? Distance over time, and distance traveled should include distance traveled by this person and distance traveled by that person. And means plus. That's why we're adding speeds. Well, anyway, that's kinematics from PY105. Or we can just visualize and memorize when they travel closer to each other, the relative speed goes up. Yes? Yeah. Yes, they're running relative to a person sitting on a ground under the tree. I'm sorry, that's my mistake. This is a tree. But a person looking at this situation from the moon would see it completely differently. A person looking at this situation from the Alpha Centauri would see it differently, including the person who is moving relative to the ground, because that person relative to themselves is not moving. So we can choose different reference frames. Resting reference frame and moving reference frame. That's basically what we are doing. Relative to that person, relative to me, when I run, the whole world travels, and the sound travels relative to the world, and the world travels relative to me. But I cannot spend too much time on this because of this. So now we know what to do. Now we can solve this equation for the frequency, which can be used here, and I'm not going to do that. Moving on. The next problem. All right, please read the problem and answer the question, because we have been practicing on relative velocities. So now we have a slightly more complicated case, because the source is moving and the observer is moving away from the source, because no one wants to be hit by a truck, naturally, and screaming at the same time, because it's scary. And if the observer is screaming, actually he becomes a source, and sometimes a driver of the truck could have been listening to that sound and become an observer. So the names of those objects, truck, person, not necessarily mean what is the source, what is the observer. It has to be, well, analyzed based on who is really listening to the sound generated by what. So both objects, depending on the situation, could have been observers or sources. So picture is already here. And now what we have is, well, we just need to add one more arrow, and this red arrow, let's say it represents the speed of the sound relative to the ground. This red arrow represents the speed of the observer relative to the ground. So, and we need to add one more arrow, the speed of the truck, which is source, relative to the ground. And because the guy travels only at 5 meters per second and the truck at 10, truck kills it eventually, unless he jumps aside. I'm just giving you time to answer the question. So the speed of the sound relative to the observer is always equal to the speed of the sound relative to the ground plus or minus the speed of the observer relative to the ground. And again, I say speed. Technically, I should have used the vertical bars representing magnitudes, but I don't like spending time on that. Same. When do we choose a plus? We know in the previous problem we did this when they travel closing to each other in opposite directions. Is this the same situation? No. So we cannot choose the plus. So what's left? A minus. And of course we would have to use the law of relative velocities, or we could place ourselves in the shoes of this guy, become an observer. In that case, the whole world would begin move relative to us, and the sound would move relative to the world, and the sound travels to us, but the world travels away from us. So that's why a minus. And the answer is, what do we have? 340 minus 10 or minus 5? 5. So 335. What do we do now? Well, now we start writing two equations. One for frequencies. And I have to choose between a plus and a minus everywhere. So for the observer, a minus. This is basically the same minus as this one. And for the source part, actually a minus as well, because the wavelength in front of the source shrink, we should decrease the denominator. And second equation, which relates speed of the sound relative to the observer, the wavelength of the sound measured by the observer, and the frequency of the sound relative to the observer. So second equation tells us how to calculate FO. 335 should be equal to 0.5 times this. And this number now goes here and done. Because we know the speeds, everything is done. 335. Well, I just solved it, so we don't need this slide. A new problem. In this situation, no, it's the same problem. No, this is the wrong word. He's so brave, he has a grenade. Well, but we know what to do, yeah? By now, everybody should know what to do. Don't answer this question. This is wrong. That's why, because we changed the direction. Because we changed the direction to the opposite. Now the closing, and the right answer will be 340 plus 5, 345. Okay. Wrong. Now, so again, faster and faster, quicker and quicker. Well, let's start from the speed. Speed of the sound relative to the observer is supposed to be equal to the wavelength measured by the observer times the frequency of the sound registered by the observer. That's supposed to be 345. That's supposed to be a half. That gives our frequency. So frequency, this, which we just have found, should be equal to the stationary case. Now, speed of the sound plus or minus speed of the observer. Oh, 5. Speed of the sound plus or minus speed of the source. For the source, nothing changed. Still in front of the source. But for the observer, now because they're closing, a plus. Done. Well, I should write it at least once. Physics is done. Well, this is a situation when a source travels as fast as a sound. So every time when the source generates a wave, it travels with the wave. This is how a shock wave generated. When a fighter jet breaks the sound barrier, that's what happens, and the strong sound wave is generated, a boom, sonic boom. And you can look up a video, nice video actually, which shows what's happening. And now we are done with everything related to the upcoming exam. So the last of the lecture time is for your questions and answers. If you have questions, you should ask those questions. If you don't, we're done. Yes? Louder, please. Any question, okay.
But I'm like, you know how if you're in a train and you throw a ball, the velocity of the ball is the velocity of the train plus what you...
No. No. You didn't say the most important part of the whole sentence. In a way you said it, there is no answer to a question. What did you miss? What did you... didn't...
Velocity of the ball relative to the...
Exactly. It has to be relative to something. So when you say relative to ground or relative to train or relative to the sun, in that case, your question has specific meaning and go ahead.
Yeah, so I'm asking, how come when the truck is moving, the sound is not the speed of the truck plus the speed of sound?
Because the sound wave or any wave is not moving in space. A wave, remember, we started from that. A wave, it looks like it is moving in space, but in reality, every particle remains at the same place, and it just pushes on a particle nearby. So as long as we created that push, that's it. It's not a ball flying away. It's a different situation. It's a push traveling away. This particle pushes on this particle, that pushes on that particle, but they don't move away from the truck. The wave moves away from the truck. You're not shooting the balls. That's a different physical situation. If you would be on a truck and you would shoot a ball from a cannon, that ball would travel away in that direction. Physical object. Here, in a wave, that's not just the case. That's not how wave operates. This would have been like if you had my slinky, which I brought, and instead of moving it end, you would take it and just throw it away, the whole thing. That's not what we're doing with waves, right? So the slinky remains at rest, but the wave inside it is moving because the turns just push on each other periodically. The process is being transferred, the energy, not the matter. Okay, you said you have another question. That's a good question. No, that's not what I said. Don't twist my words. What I said is that if there is a wave traveling toward the observer, no matter how it was generated, it could have been generated by a stationary source, it could have been generated by a moving source. No, it doesn't matter. What matters is that both observers resting or running would measure the same wavelength. That was my statement. This wavelength, in turn, could have been affected by the moving source. Maybe not, if the source would not be moving. That doesn't matter. What matters is these two guys measure the same number.
It doesn't matter if the source is stationary.
You're trying to compare two different things. So this is the number one, this is the number two. The wavelength measured by a resting observer, the wavelength measured by a moving observer. These two numbers are identical. There is a number one, and there is a number two. This number represents the wavelength of a stationary source. This number represents a wavelength of a moving source. These numbers will not be different, will not be equal, they will be different. So again, when you say this word wavelength, you must be absolutely accurate and absolutely specific. What do you compare to what? You have a question. I know you do.
One of the problems in part 3 of the homework, the one that has the many directions of the wires. I was wondering if the example.
So a problem like this, I don't remember the number, we went through this problem in great details. If anybody has a specific question about this problem, we can talk about it. But that was a good example because some student named this problem crazy, and I disagree. This problem just requires many steps, not 2, not 3, well, maybe 9. But you know, you just have to start walking and walk in the right direction. But the question is related to the difficulty of the problems, and a difficulty is a number. We have to compare two numbers. The number which represents the difficulty of homework or class or lab problems, and another number which represents the difficulty of exam problems. What do you think? All right. What do you want? Well, I have my personal approach, which is very simple, and for me is very natural. The exam problems should be harder than the easiest homework problem, but easier than the hardest homework or class or lab problem. That's it. That's what I try to do. That's my intention. How it happens, it's out of my hands. You had a question, I think? No? Any questions, please? If you have no question, you're free to leave, of course. We're done. If you have a question, you can ask a question. All right. Just be louder now because people start moving.
When you're calculating the wavelength of the observer, and the observer measures, you have to use the relative velocity.
We have, in general, two relationships with wavelength in it, right? So number one. And when we write it, we can use the speed of the sound relative to the observer, the wavelength of the wave measured by the observer, and the frequency of the wave measured by the observer. Or the same equation also relates frequency and wavelength. Nothing here, but a couple of cards downstairs you can bring, please. Thank you. And in this case, V represents the speed of the sound relative to the ground. Wavelength represents wavelength measured by a stationary observer from a stationary source. Frequency represents frequency of the sound measured by the resting observer from a resting source. That's it. That's what it is. So you have to say it in your mind or even out loud. What does every letter represent? And then assign a number, well, which you have given to you correspondingly. And the second, well, this is one equation, two faces, but another equation which we haven't used, could have been using. We used it only once at the beginning to derive the expression for the final expression for the frequency. Algebraically. And then we forgot about it. We never use it mathematically for any problem. But we could have, it wouldn't change a thing. I just don't see a point. Because those equations, if you use it right, tell everything much faster. Yes?
You know the equation when we have the force of tension and the density of the string?
Yes.
So for that equation, we find the speed for the oscillation.
No. This equation tells us how to calculate the speed of a wave propagating on a string. Again, similar situations. Every particle moves, of course, but it doesn't travel away. It moves about the equilibrium position. And at a certain point, when it travels through the equilibrium position, it reaches maximum speed, but that is not a speed at which wave travels in space. Wave travels in space normally much faster. And this is how we can calculate the speed for the wave on a string.
But if I asked this question before, if it's a standing wave, it has the same velocity as the moving wave that created it. Yes.
When we have a string, we can generate any wave, standing, sinusoidal, more complicated. The shape doesn't matter. If we have a string with this tension and this density, and we start exciting it at a certain point, where we apply a function generator. From this point away, the process, the energy begins traveling. The energy begins traveling with this speed. That's it. But sometimes if we excited several waves in a specific manner, which travel, we just don't see them. What we see is the result. The result doesn't move. The result doesn't move. But under certain circumstances, when wavelength and the length of the string have special values, but it doesn't mean that the waves in that string can't move at all anymore. No, they still move and still with the same speed.
And that speed we find is the same value if we just multiply the wavelength of that wave.
Exactly.
The frequency of that wave.
That's, well, technically we started from this. That's distance over time, which is this. So this is a string. That's what you start from, an actual physical object. You start exciting it. And there is a propagation of energy. And this is how fast it propagates. Everything else comes on the top of that. No matter if you start exciting more waves or less wave or wherever, as long as you keep the same string, the same tension, they will all travel with the same speed.
Let's send a picture to you, right? And it's just a picture for that one. I just want to make sure it was just a picture of that one problem that you wanted.
What's the question?
You asked us to send a picture.
Yes, I did.
This is for that one problem?
Yes,
Okay.
just for that one problem.
One more question before you shut down.
Yep.
So the Vmax we find there,
Yeah.
that we can't find that Vmax with the frequency and the wavelength. That's a different.
No. Omega is related to frequency. Omega is 2 pi times this frequency.
Okay.
But it also relates it related with amplitude, yeah, because it.
So is the speed equations are the same no matter if the wave is a transverse wave or the other one?
This is a speed for the maximum, and that is the same. This is the speed for a wave on a string. So you cannot excite longitudinal waves in a string. That's impossible.
Yes, yes. No, I was just thinking for the speed of sound calculation.
Well, the string excites molecules, and that's what makes a sound. The speed of the sound and the speed of the wave on a string are different speeds. They have the same frequency because when the string vibrates, it starts pushing on molecules, and those molecules push on other molecules, and this is just a physical interaction, force on force. So when a string vibrates, the frequency it has being transferred to the frequency of the sound, but the sound will travel with a different speed, the speed of the sound. This is just, this equation only can be applied to a string for calculating the speed of a wave on a string.
And for the speed of sound equations, you can't change the speed of sound, right? You just can't change the relative speed of sound because we have physical objects moving.
I'm not sure what you mean. We can, in general, change speed of sound in air by changing pressure or temperature.
Yes, but with changing frequency and wavelength, we can't, right? Because when we change the wavelength, the frequency is automatically going to change because the speed of sound is constant.
Relative to the ground.
Yes.
Or relative to the observer.
Yes. If the observer, I understand.
Doesn't matter. This relationship, well, it's already here, works no matter what, for any situation. And the speed, this speed, is defined by the conditions. So it's given 330, 340.
For a certain temperature.
So it assumes the certain temperature, certain pressure, and this number assumed relative to the ground. But if you have an observer who is moving, that person will measure a different speed, that's it.
Yeah, okay. And for the sonic booms, does the boom happen because the waves traveling this way make a constructive interference? Is that why you hear that?
Well, it is a constructive interference because basically they all being generated at the same place now, so they kind of adding up.
Have add up in a conical shape. Right?
Yeah.
And then they.
Yep. Then
construct.
Yep. If you look at, well, you probably can find someone on YouTube, you know, on a scooter. People drive a scooter on water. You can see exactly the same situation because speed of waves on the surface, relatively slow, you know, relatively low. Water, well, so those waves, I don't know, maybe 10 kilometers per hour. So you can drive as fast as those waves, and you can see behind the cone.
Oh, it's the same.
It's the same.
I was just curious. I was looking.
Yeah.
At